Dear students, greetings for the day. In this class, before going to the showing the motion of the projection of the particle on y diameter of the circular SHM, let us recapitulate the previous class topic, that is definition of simple harmonic motion and examples for SHM. So simple harmonic motion is the special case of periodic motion. Periodic motion means the motion of the body which repeats after certain time interval is known as periodic motion of the body. For example, motion of the moon around the earth and motion of the earth around the sun. So moon repeats its periodic motion after every 30 days. And similarly, earth repeats its motion around the sun for every 365 days, that is after 12 months. Now, simple harmonic motion is defined as the motion of the body, periodic motion of the body along the straight line such that its acceleration is directed towards the mean position and is proportional to its displacement. So, the motion of the body along a straight line, the to and fro motion of the body along a straight line such that its acceleration is directed towards the mean position and is proportional to its displacement is known as simple harmonic motion of the body. Examples, certain examples are motion of the cradle is simple harmonic, and motion of the simple pendulum is also simple harmonic, that is oscillations of simple pendulum are simple harmonic, and the motion of the vertical loaded spring which is stretched and leave it, then the oscillations made by the vertical loaded spring are simple harmonic, and the motion of a ball on a concave surface is also simple harmonic, and the motion of liquid or oscillations of liquid in lead tube are also simple harmonic. These are the certain examples. And the needle of the sewing machine is also simple, the motion of the needle of the simple harmonic. So the motion of the needle of the sewing machine is also simple harmonic. Now, again, we shall recap the conditions of SHM. So, for every motion to be simple harmonic, the body must satisfy certain conditions. First one, the motion of the body should be periodic. Second condition, the body must execute to and fro motion about its mean position. Third condition, the acceleration of the body is always directed towards the mean position. Fourth condition is acceleration and displacement of the particle are opposite to each other. Fifth condition is restoring force acting on the body is always directed towards the mean position. So, the motion of the body should be periodic, and the body must execute to and fro motion about its mean position, and the acceleration of the body is directed towards the mean position, and acceleration and displacement of the body are opposite to each other, and restoring force is always directed towards the mean position of the particle. These are the conditions of the simple harmonic motion. Now, let us show that the circular motion of projection of a particle on x diameter and y diameter of the circle is simple harmonic. When the consider the circle of radius r and main position O, then consider the particle moving along the circumference of the circle of radius r and center be O. So here when the body is at A, its projection on y-axis is at O, and if the body moves from A to B, then its projection moves from O to this N, and when the body moves from B to Y, then the tip of the projection moves from N to Y. When the body moves to X dash from Y, then again projection moves from Y to O. When the body moves from Y, X dash to Y dash, then its projection moves from O to Y dash. And when the body moves from Y dash to X, then tip of the projection moves from Y dash to O and again reaches the same starting point, and then motion repeats. So when the body is initially at A, then its projection on Y diameter is at O. Next, when the body reaches to point Y, on vertical Y diameter, then tip of projection reaches to Y. See, when the body to the point X dash from Y, then tip of projection moves to O, from Y. Yes. Next, when the particle reaches to point Y dash, then its projection on Y diameter moves from O to Y dash. So when body moves from X dash to Y dash, then the tip of the projection moves from O to Y dash. when the body reaches to the starting point A, the tip of projection reaches to X from Y dash. And the body repeats its motion. As the body completes one revolution, again tip of projection repeats its path O to Y, Y to O, O to Y dash, Y dash to O. Along with the body. Along with the body. As the body completes one revolution, again the tip of projection repeats its path O to Y, Y to O, O to Y dash, and O along with the body. Therefore, we can say the projection of the tip of the projection moves on the vertical diameter about the mean point O is simple harmonic. Therefore, we can say that the projection of circular motion on any Y diameter of the circle is simple harmonic. Therefore, here we consider the vertical diameter OY, Y dash. So when the body is its vertical projection is at O, when the body moves to Y, then tip moves from O to Y, and when body moves to Y to X dash, then the tip moves from Y to O, and when the body moves from X dash to Y dash, tip moves from O to Y dash, and when the body moves from Y dash to a starting point on X diameter tip, then again tip moves from the starting position O. from I dash, and again the body moves like this, and the motion it again repeats after the time period. So here the projection of motion of body on the diameter is a simple harmonic. Now let us derive the equations of SHM. Now let us derive the expression for x displacement and y displacement of a particle executing SHM, or as these expressions are also known as equations of SHM. So now let us derive the equations for SHM. Therefore consider a particle moving along the circumference of the circle of radius r and center B O. And the body moves from A to B in time t. After covering angular displacement, therefore here x displacement be OM and y displacement be ON. So on x diameter, x displacements of the body when it is rotating along the circumference of the circle, and also y displacements are in on y axis about mean point O. Time t. Therefore, from figure, from triangle OMB, from right angle triangle, sin theta is equal to opposite side BM by hypotenuse OB. That equal to BM is equal to y displacement. Therefore, sin theta is equal to y by OB, or y is equal to r sin theta. That equal to theta is omega t plus phi, where phi is the approach and omega is the angular velocity and t is the time. So the displacement covered in unit time is called angular velocity, angular displacement by time. Therefore, r into sin omega t plus phi. This is expression for y displacement. Therefore, it is number equation y. And from the same figure, cos theta is equal to adjacent side OM by hypotenuse OB. That is x by r. Therefore, x is equal to r cos theta. Therefore, x is equal to r into cos omega t plus phi. Let this be equation 2. Equations 1 and 2 represents the y expression for y displacement and expression for x displacement of a particle executing SHM. Therefore, equations 1 and 2 are known as called equations of SHM. So these are the expressions for so from this right angle triangle OMB. So x displacement is obtained by drawing the projection, vertical projection on x diameter to get x displacement O to M. Similarly, to get y displacement, we draw the projection from B to y diameter, that is N, and ON gives the y displacement. So from right angle triangle OMB, cos theta is equal to opposite side by hypotenuse. That is BM by hypotenuse OB or Y by R. Therefore, Y equal to R sin theta or R into sin omega t plus phi. This omega t is equal to theta is equal to omega t plus phi, and cos theta is equal to, from the same triangle, Ym by OB or x by R, or x equal to R cos theta or x equal to R cos omega t plus phi. So these two equations are nothing but the expressions for y displacement and y diameter, and equation 2 is the expression for x displacement and x diameter. So these equations 1 and 2 are known as equation of SHM. Now let us derive the expression for velocity. So here at time t is equal to, this equation becomes y equal to r sin omega t. So here y r sin phi, that is, it represents the initial displacement at time t equal to 0. y0 is equal to r sin omega sin phi. That is the initial displacement at time t equal to 0. Now consider vertical diameter only. Therefore, velocity of the particle on y diameter. Therefore, expression for y displacement is already we derived that y equal to r sin omega t plus phi. Now we want the expression for velocity. So velocity is the rate of displacement. Therefore, dy by dt in time interval dt at the displacement by dy. Then, so change in position by time is equal to velocity. Time interval d theta. Therefore, since r is a constant, r into d by dt of sin is equal to minus cos. Therefore, minus r into, this may be written as r into minus into d by dt of omega of t plus phi. Therefore V equal to, this is r omega, phi is constant 0, therefore r omega, r into omega into cos omega t plus phi. Now this may be written as r omega, cos is written as 1 minus sine square and square. Therefore r omega into sine omega t plus phi is nothing but y by r. From this expression, sine omega t plus phi is equal to y by r. Therefore r omega t into under square root y minus taking LCM, r gets cancelled, omega into r square minus omega y square, r square minus y square. So this is the expression for y displacement. Similarly, from the y displacement, velocity in the of the particle on y diameter is omega into r square minus y square. Similarly, from x is equal to, from x displacement, x is equal to cos omega into omega t plus phi. Therefore, from that Vx is equal to, we may write similarly therefore Vx is equal to similarly omega into under square root r square minus x square. Let this be fourth equation. On x diameter, the velocity of the projection of the tip of the motion of the body along the circumference of the circle is omega is equal to, from this expression we obtain like this, velocity of the particle is omega into under square root r square minus y square. That is, similarly x velocity is equal to omega into r square minus x square. So from these expressions, maximum velocity is obtained at O when r is equal to, here y displacement is 0 at maximum velocity, that is y displacement is 0 means here at 0 is equal to 0, and at the tip maximum velocity is 0. Therefore when r is equal to y, therefore maximum velocity is equal to 0 at the tips of the y diameter, and at center mean position velocity is maximum. V equal to r omega when y equal to 0, then Vy maximum is equal to for maximum velocity is obtained at y is equal to 0. Vy maximum is equal to y equal to 0. Therefore, V equal to R omega, and Vy minimum is equal to 0 at R is equal to Y, at Y equal to R. Similarly, Vx, Vi also. Maximum velocity Vx is equal to R omega at x equal to 0, here mean position, and Vx is minimum at tips of the horizontal diameter. Now let us derive expression for acceleration of the particle executing SHM. So acceleration always acts towards the center. Mean position. Therefore, angular velocity is represented by omega and angular acceleration is represented by alpha. Therefore, here we want to get angular acceleration alpha is obtained by rate of change of angular velocity, or d by dt of y. Omega means dy by dt. Therefore, d square by dt square into y. Substituting the value of V by R omega cos theta, so here Vy is equal to R omega cos phi. And simply we take the value of Vy. R omega cos omega t plus phi. So cos equal to minus sin R omega, as these are constants, d by dt of that equal to minus sin. Therefore, R omega into minus sin omega t plus phi. by substituting here sin omega t is equal to y by r. So minus omega into here into d by dt of omega t plus 5. This, therefore again here omega is there, therefore omega d by dt of d omega t plus d by dt of 5. d phi by dt is, as phi is a constant, it is 0, and omega is constant. Omega into dt by dt is 1, therefore omega into omega, this omega into omega, omega square into r sin omega t plus 5. This is nothing but y, therefore minus omega square y, this figure. Already derived expression for y displacement from equation 2. Therefore angular acceleration is equal to minus omega square y. Therefore angular acceleration omega is equal to minus omega square by y. In the case of x displacement, this is minus omega square x, and maximum value of angular acceleration, maximum acceleration is equal to at y is equal to r. Therefore r omega square, nothing but that is at tips, here y is equal to r, at the tips of the diameter we get the maximum acceleration. Minimum acceleration is at 0 and velocity is maximum at 0. Minimum acceleration at y equal to displacement 0. Therefore minus omega square into 0, 0. These are the expressions for angular acceleration is equal to dv by dt, and we consider y diameter displacements d by dt into expression for velocity of the particle excluding SHM on y diameter is given by r omega cos omega t. On simplification we get minus omega square y. Therefore maximum acceleration is at y equal to r omega square, and the minimum acceleration is y equal to 0, therefore 0. We take here only magnitude, because here minus sign indicates the acceleration and displacement is opposite to each other. Therefore acceleration is positive direction. If we take, then displacement is minus y, omega square into minus y. So from this table we consider the particle moving with velocity v, and the velocity of the particle along this y diameter is given by r omega cos omega t plus 5. Therefore by taking the derivative of r omega cos omega t plus 5, it is equal to r omega is constant, therefore r omega into d by dt of cos omega t plus 5, and this r omega, this is minus sin omega t plus 5 into d by dt of omega t plus 5 angle value. Now this is equal to d d omega into dt by dt, that is 1, omega plus 0, dy by dt is 0. Therefore, by substituting here omega into sine, omega into omega, omega square, r is written inside, therefore r into sine omega t plus 5. This minus is written outside. This is equal to y value, therefore minus omega square into y. Therefore maximum acceleration is obtained when the y displacement is equal to its radius, that is r omega square, and the minimum acceleration is obtained at displacement y equal to 0. Therefore, if y equal to 0, then acceleration is also equal to 0. Therefore, acceleration of the particle n, that is tip of the projection on y diameter is so in this class we derived the expressions for equation of SHM and velocity of the particle executing SHM and acceleration of the particle executing SHM. In next class we shall continue to derive expression for time period of the particle executing SHM and frequency of the particle executing SHM.